So, ladies and gentlemen, actually I'm going to talk in English to let my colleague in a faraway place on Earth, who is joining us via Zoom, to let him understand what I'm saying more easily than through an interpreter. First of all, I'm very much honored to be invited to the National Museum to this excellent conference. This is the 10th conference of the MuseumDigit series, and I think it is getting better and better every year. This year is completely renewed, and I owe my congratulations to the organizers. The second thing is I'm also much honored on behalf of the Semmelweis Museum that we have contributed to the organizing of the conference in terms of finances with a considerable sum. This lecture will be in two parts, and not only because my colleague, my Greek colleague, will talk through the Zoom, but also he's going to speak to you about the technical details which this project is aiming and which is the objective of this project. And I'm, as a kind of an introductory note, I will tell you something about how this whole project was developed and why it is important, and what are the dangers, I would say, the ethical problems with all kinds of artificial intelligence applied into exhibitions and into the museum world. The project is consisting of, I think we are about 14 nations, 14 institutions and 9 nations or 9 countries are involved in it. There are two types of contributors. One part are collections. These are party museums like the Semmelweis Museum of the History of Medicine, but also the National Library of Romania from Bucharest, also the Balkan Museum from Serbia, and also there are some people who present the Stadtliche Museum to Berlin. On the other part, there are those who are the IT experts, but they are more numerous. So there's this 4 to whatever. So the IT experts, and the IT experts are still two categories. One part of them are at universities, teaching various kinds of digital technology, especially, obviously, artificial intelligence. On the other part, on the other type of the contributors are private enterprises from Germany, Sweden, Spain, England, the United Kingdom, Greece, and many other countries. The aim of this project, and it is called SHIFT, and is supported by the Horizon Europe scheme of the Union. The original idea of the project was how we would be able to introduce, nem mozgassam. Okay. How we would be able to introduce artificial intelligence into museum exhibitions. Now, some of you know me in Hungary and some internationally for ages, and I think many of you know that I'm quite an ardent opponent of applying digital technology in exhibitions. And there is a good reason for this. If the visitor is an exhibition which is full with digital technique, which is full with possibilities from QR code up to screens and so on, then this kind of intimate relationship which the curators are aiming to achieve, an intimate relationship between the visitor and the object which is single one, which is non-repeatable, which is unique, it is practically destroyed. Because people's attention will turn, obviously, towards the IT technology. So I think, just imagine that when you are standing in front of a very rare painting, and instead of watching the painting in reality, on the other part of the world, for which you paid lots of money to arrive there, and you are reasonably not tired, and instead of watching the painting, watching the art object, you are paying all your attention to a screen. You can do it at home, on the plane or whatever. So that's not much point in it. So I'm not very keen on it. It doesn't mean, nevertheless, that in all the rest of the museum work, so cataloging and the databases and online accessibility and so on, that is a very important part of IT technology, but I think that not really in the exhibitions. Now, in this case, when I decided that we are going to join this consortium, I changed my mind, and I changed my mind because the aim was quite noble. The aim was that how, if you could use artificial intelligence to make accessible all collections to those people, to those of all visitors who are practically, how to say it, sight or visually impaired, colorblind, who just cannot get the same information normally from the object itself, and the help of IT technology, and especially artificial intelligence, could help them to understand and to achieve, or to reach the meaning of these items. So that was the main point, and I think it's ethically it's a very well-founded point. And then comes the next point, that how far we can go with. So there is an integrity of the objects, obviously. So you can't do anything with the objects. So if you use AI for changing the atmosphere of the painting or the sculpture of a drawing or whatever object, then perhaps the integrity of the original author, of the painter or the sculptor, of the artist, is simply changed, and we just cannot do it. So what are these small lines, I mean, ethically speaking, which are between making it more accessible, more understandable to handicapped people, whereas we are trying to keep the totality of the meaning of the object. And then came yet another point of view, and that's what our lecture will be, and that's my colleague Philippos will tell you in detail soon. And that was when we realized that there is very small objects which you just cannot present to the visitors in exhibitions. And then we selected coins. You see, the problem with the coins is that the coins, if we are not talking about the money, but about the coins which are representing something called the commemorable coins, is that they are just beautiful. They're full of information from the various ages. There's a very strong iconography of them. Art historians usually don't really care about them because they're too small and unimportant, so there are very few of them work on them. But the information which could be gained from these coins is just enormous. Yet, we cannot present them because they are so small. I mean, everybody practically would die going through an exhibition of, say, 300 or 3,000 coins. You just can't watch them. So, and then came the point that what if we use these new technologies, these kind of state-of-art technologies which we are able to use, what if we apply them for presenting coins in exhibitions and certainly online? So how we can make these very small items, very small things on these small artificial objects to make more visible, more understandable to the public. So that's what my colleague Philippos is going to tell you, because we've been working on it since, well, practically since May, so we are not very long time ago, but some time. And we have some achievements already, we had to, after all. And so forth, I would like to give the floor to my friend Philippos to tell you all these details. Thank you for your attention.
Greetings to everyone. Hopefully you can hear me. And if any problem comes up, just let me know. I'm grateful for this chance to share our work. So I'm Orphanoudakis Philippos, specializing in machine learning. Recently, I joined the European project SHIFT, focusing on the preservation and promoting of our cultural heritage. And today, in this context, I will be discussing 3D modeling of 2D objects in coin datasets and an innovative pipeline for the extraction of distorted details. So to provide a clearer overview of our coming discussion, we'll be delving into 2D images of cultural coins commonly found in museums. These images often exhibit outer details that aren't easily discernible to the naked eye over time. So our aim is to develop a pipeline capable of distinguishing small foreground details from the background. Through the creation of segmentation masks, we can effectively isolate these details for further processing. So our reliance lies on the accuracy of our segmentation masks, and leveraging a deep learning architecture, we aim to generate multiple perspectives from a single 2D representation, facilitating the modeling of the 3D objects. For instance, here's an example showcasing distorted details In the original image, you will notice faded letters and almost vanishing objects, illustrating the alteration over time. So why are we doing this and what's the motivation? So the driving force behind our endeavor is to extend the experience of exhibit details to a significant portion of the population grappling with visual impairments. So by enabling access to these details, we aim to bridge the accessibility gap. Moreover, our efforts contribute to digitization of exhibits, facilitating the creation of a comprehensive digital library. So this tool serves as a valuable resource in preserving cultural artifacts for future generations. Ultimately, the added utilization of these tools holds the potential to significantly contribute to the conservation efforts and deepen our understanding of these exhibits, potentially unraveling greater insights and historical significance. So how are we going to do all the things that I've mentioned? So to accomplish the mentioned objectives, we're heavily reliant on the Semmelweis Museum, which generously provides us with images of their exhibits, granting us access to real case scenarios. And also, our methodology involves the utilization of deep learning architectures through synthesis, fine-tuning, and training. We're going to construct an offline tool tailored for post-processing needs. So at the outset, our pipeline comprises 3 distinct stages, each rooted in a pre-trained deep learning architecture. So our initial phase involves super resolution, aiming to enhance imaging quality, leveraging the ESR GAN model. Subsequently, we implement the segmentation phase using the segment anything model, followed by employing the 1, 2, 3, 4, 5 model for the 3D modeling stage. First of all, ESR GAN, an advancement over the traditional SR GAN, operates on a convolutional neural network. Its design specifically targets image enhancement by augmenting the resolution. Its objective extends beyond pixel level enhancement, striving to produce visually captivating and authentic images by capturing small details. ESR GAN showcases remarkable advancements in generating high-quality images, particularly in texture, sharpness, and overall visual realism, surpassing conventional methods. Points exhibiting large gradients correspond to object differentiations, where in our observation, when we deploy the model, ESR GAN notably enhances these crucial areas. Finally, we'd like to mention that when deploying, it's very crucial to consider the denoise parameter. Excessive smoothing and denoising might distort the sets of features and details, so we must pay real attention during the application. In the subsequent phase, we implemented the segment anything model developed by Meta AI, renowned for its zero-shot generalization capability. So this model's strength lies in comprehending a broad understanding of objects, enabling to generalize seamlessly to unfamiliar objects and images without requiring additional training. So this capability represents a significant advantage for addressing a very specialized problem. Although SAM has been initially trained on an extensive dataset, over 1 billion segmentation masks, we wanted to tailor to our very specific dataset. So for this case, for this goal, we employed the WorldCoin dataset, a non-live public dataset, curating a new dataset featuring the 300 points alongside the corresponding 300 segmentation masks. So we retrained the model, and during this training phase, we utilized dice loss. So dice loss is very important for us because it emerges as particularly effective in addressing class imbalance within data, a real challenge in segmentation tasks, where the background class tends to dominate in pixel count compared to the foreground class. Additionally, it demonstrates robustness against noise and minor local variations in segmentation masks. So this resilience renders dice loss as a favorable choice for handling noisy or low-resolution images encountered in our context. So in the last stage, after confirming the high quality of the segmentation masks, we expand our methodology by incorporating the 1, 2, 3, 4, 5 architecture to capture 3D perspectives. So specifically, this model represents an integrated process for constructing 3D multi-view messages. This model is easily deployable and does not require many resources, as it is single feed forward pass, unlike many traditional models. but it needs to be mentioned that currently the model works for sizable objects like figures and heads and not for smaller ones. So in the upcoming slides, we'll showcase 5 examples illustrating the efficiency of our pipeline in segmentation tasks. To provide the basis for comparison, we have incorporated 2 additional models. Firstly, YOLO V8X, while not specifically designed as a segmentation model, it stands as the state-of-the-art model for object detection. And secondly, PSPNet represents the state-of-the-art in this domain. So this model will serve as benchmarks to evaluate and contrast the performance of our pipeline. The layout for each example remains consistent. The initial image displays the original, followed by the outputs of YOLO and PSPNet. Additionally, 2 images in the bottom row showcase the results generated by our proposed pipeline, providing 2 viewing options according to the individual preferences. It's noteworthy that every detected object can be isolated or segmented further as needed. So yeah, this comparison allows for a comprehensive assessment of our pipeline's performance alongside established models. I will give each example a few seconds on the screen just so everyone can see them clearly. Just to mention, in this particular example, we are presented with a more challenging scenario, and notably YOLO fails to detect the object entirely, or may even misidentify the objects in it. A trend we'll observe across subsequent examples. Okay, going to the next example. And just to mention, in this final example, our pipeline really handles all the letters that are presented, which is quite impressive. Yeah. So in the upcoming slide now, we'll showcase 5 additional examples demonstrating the outcomes of our 3D modeling algorithm. Before inputting data into the model, we initially generate the segmentation mask and isolate the object. So this process leads us to the stage where we can provide input to the model for further processing. So we start with an example of a head, which we first extract with the segmentation masks. Here's an example of 3D modeling of the top part of the body. Here's an example of a full body. And maybe more complex example with the top half body with a hat. And finally, a really complex top half body. So yeah, thank you everyone. And hopefully it was everything was really understandable. But yeah, thank you.